It's a cooperation between University of São Paulo and Liverpool School of Tropical Medicine. So where's the, So then just a brief introduction about what is malaria. We already saw, but let's see the life cycle of the disease. So infected mosquitoes infected a human being, that the sporozoites goes to the liver. In the liver, after this phase, it's introduced in the blood stage, where some gametocytes are produced and infect again the mosquitoes. And then the mosquito can infect another person. For malaria vivax, we have one peculiarity that in the liver, the human being can store some hypnozoites, and as Lisa already said, it can relapse afterwards. In Brazil, we have this very peculiar pattern of malaria. In 1960, we had malaria all around the country. Now in 2014, we have it concentrated in the Amazon Basin. Like after around in the 80s, we had this very sharp peak of malaria, and after this, it was introduced the National Malaria Control Program, which reduced a lot the number of cases, especially death, related to malaria. This sharp peak here is mainly related to two main things. Gold mining in the area of Amazon. Here we have Serra Pelada. So a lot of people from the south moved to the north to gold mining. We have some pictures, very bad house conditions, which spread a lot of malaria in the area. And also some big constructions. Here we have the Trans-Amazonica Highway that crossed the Amazon Basin. So this kind of constructions also brought to the Amazon Basin a lot of people that were that didn't have any immunity against malaria, and then it increased a lot of the number of cases. Right now, according to the Minister of Health, we have this map. Malaria is concentrated then in the Amazon Basin with very small hotspots. Yeah, the cities here are really big, and then they are located just around this area in the Amazon. One very interesting fact about malaria, different than what I would say we have in Asia and in Africa especially, like malaria in Brazil is a notifiable disease. So every case that is registered here, that is diagnosed and treated in Brazil, is notified and enters in the system of the Minister of Health. Also, the treatment is just done in the public system. You cannot go to a private clinic and diagnose and treat malaria. So in this scenario, we can assume that we have really good data to deal with. One of the main hotspots in Brazil is the Juruá Valley, located in the state of Acre, and here we concentrated our study. So this work here is part of this main project, the ICMR. ICMR stands for International Centers of Excellence for Malaria Research. It's founded by NIH, and we intend to study urban malaria. That is a new, is something new in the world. Usually malaria was mainly in rural areas, and now we can see already transmission in urban settings. So we try to understand this. So in this ICMR, we are studying malaria in different parts of the world. Here we focus in Mancio Lima. So then going to the project. So we know from many infectious disease this heterogeneity in transmission, and there is this paper from 1997 from Woolhouse, and he observed this 28 rule, he's calling 28 rule, which says that 20% of the host population contributes at least to 80% of the net transmission potential. This is something that we had in mind to construct our model. He saw this for example, HIV and other diseases, including malaria. It was already seen in Africa, children, this pattern as well, this 20-80 rule. So this heterogeneity is due to many different sources. For example, there are behavioral characteristics, different levels of attractiveness to mosquitoes, partial immunity, and other factors. And regarding our study setting, we already found some risk factors in the area, characterizing this heterogeneity in transmission. So then we want to build a very simple SIS model and try to incorporate some features in the model, and we want to describe how the transmission is going in this area. So the material we have for this model, like first we made a population census in the city. So city is located here. And we got information about everyone in the city, and we got individual and household information. We also got from the government all the cases diagnosed in the city from October 2015 to September 2016, which is almost the same period as our population census. And then from this data, we could find around 2,000 cases. The majority of cases is due to P-vivax, just 193 due to P-falciparum, and we have this age distribution. We restricted our analysis just to P-vivax because P-falciparum is not playing, it has just few cases, and then we just consider this P-vivax. Also because we didn't have many people above 80 years old, and it was introducing a lot of noise to our model, we excluded them. And then we got two main data sets which we are going to try to fit with our model. What is it? The incidence density stratified by age and the number of cases per individual. So it means that we have data from everybody, and then we can count the number of cases per person. This is kind of a unique data set. So let's start trying to fit this data set. We start with the most simple model, SIS, and then with this kind of model, of course, we cannot fit this data set. Because, so then we introduced an age-dependent force of infection and partial immunity acquisition to try to describe this. Introducing the age-dependent force of infection, then we went to the literature and got this formula here that correlates the body surface with the probability of getting infected. So it means that if a child that is much smaller than you is close to you, and then comes a mosquito, just because he has or she has a very small body surface, is going to have a lower probability to get bitten. So this has this curve, this shape. Yeah, this formula has this shape. And then when we introduce it here, we can correct the first part. We cannot correct the second part. And then for the second part, we introduce this partial immunity factor. So for the partial immunity, after each infection, we are assuming that a person that got infected is getting a small level of immunity, yeah? So then we had to open this and then make, and in this case, an infinite number of equations. Of course, due to the force of infection we have in this place, we don't need to go to the infinite. After some point, we don't have people anymore moving forward. So then with this, here, we consider an exponential decay for the force of for the partial immunity, and then we can correct the second part of this data set. We can see that with this formula here, for a naive person, of course, this is 1, then the partial immunity is not playing a role. But with this formulation here, we can fit relatively well this data set, but the number of cases per person is not that good. To correct this, then we introduce a risk distribution. For a risk distribution, we try to make as simple as possible, because we don't know, like, this is a gamma distribution, this is a log normal distribution, a normal distribution, we don't know. And then for it, we just consider, like, we add this risk factor for this group, and then we consider another group with a different risk factor. Yeah, so we are assuming that we have a low risk group and then a high risk group. And for this, we consider this kind of distribution that summarizes any other type of distribution that we don't know exactly the form. Then, like, we are saying that we have a proportion of people under high risk and a proportion of people under low risk. This distribution is constrained to this set of equations. So, of course, the proportion of the low risk group and high risk group, the sum is 1. We are assuming that the mean value of this, the risk is 1. It means that we are not controlling the force of infection with this risk distribution. The force of infection is controlled just by lambda, which is the force of infection. Yeah. So then with this, we fit the model, and to fit the model, we went to this paper, we talked with these guys, and then we assumed that the residuals of our fitting, yeah, are normally distributed, and then we have this likelihood, and then we try to minimize. So, but here we have 2 different data sets. We consider both likelihoods, and then by minimizing, then we started with 30 optimizations for each risk distribution. So we consider, based on that first paper I showed you, talking about this 20-80 rule, we consider different proportions of individuals in the high-risk group. And then we saw that after optimizing our model for different risk distributions, we found these 28 rule as well here, like 20% of people are under high risk and 80% of the people are under low risk. This gave us the best log likelihood. After 3 weeks running in a computer with 50 cores, we got the confidence intervals for our parameters, and we can see here that we don't have many parameters. Yeah, we have a system with many equations. Yeah, ideally is infinite, but we don't have to go to infinite, of course. And then we just have those parameters. Yeah, and then we got this. And if we see the dynamics of our model, we can see that the low-risk group, people are moving through compartments really slowly. Like here we have age, yeah, and here the proportion of people. So the naive people is decreasing really slowly, while in the high-risk group, people are moving really fast between compartments. Here we have susceptibles and infected individuals. And here is our fitting, yeah? This is the fitting for the incidence density that is composed by the high-risk group and the low-risk group. And here the number of cases per person. The fit is quite well, I would say. For this fitting, then we have this risk distribution, this force of infection dependent on age, and this partial immunity level. Yeah, great. Then we went back to our model that was this with 2 groups. Yeah, J here is 1 or 2. And then we made one assumption. And this, I would say, is the biggest contribution of this work. So our assumption is immunity does not alter individuals' exposure. What does it mean? Yeah. So if a guy is here, the probability to become infected is reduced by the partial immunity, right? Like this sigma 1, sigma 2, and it's increasing. But the guy that is not coming here because of partial immunity, the probability that a mosquito come and beat him is not changed. Then we introduced these new compartments to our model. So here we have the complementary proportion of people. Yeah, like some people is moving to become infected. Those that were bitten by mosquitoes and are not affected because of the partial immunity are becoming asymptomatic. An asymptomatic infected person can also become infected again and recover and so on. Look that here we are just opening this compartment here, but people moving through the compartments forward is not changed compared with our previous model. But here we have one big issue. We don't know for how long an asymptomatic person stays in that condition. Let's try to deal with it. How did you do? So here, just look into our model, and then if we just assume for now that a person stays asymptomatic for 90 days, we have this, and this is really interesting. Like the asymptomatic compartment of the low-risk group is almost zero. Nobody's getting asymptomatic if you are under low risk. But the high-risk group is becoming asymptomatic due to the partial immunity that they are acquiring. Yeah. But then we tried different scenarios. So we said for 30 days, for 90 days, or 180 days that a person that is asymptomatic will become asymptomatic. And then our model predicted these values here, which is according to the literature. As older as the population, as higher as the prevalence of asymptomatic infection. Yeah? If we increase the values as we increase it here, we increased the proportion of asymptomatic infections prevalence as we have here. So it's kind of like in the literature, we see that we are not far from those values. Like we have 80% of asymptomatic infections in populations where we have low transmission rates as we have here in Brazil. We also can, instead of doing this, put those values in this axis and vary this from 30 to 180 and make an integral over this curve and calculate the prevalence in the whole population. So then from 30 to 180 days, we vary the prevalence of asymptomatic infections from 1.5 to around 4.5%. This is mainly due to the high-risk group. Yeah, the low-risk group, there is almost no asymptomatic infections. And then if you remember the model, yeah, like we have S, I, S, and so on. We don't have a latency periods or in other compartments. We try to make it as simple as possible. So we are assuming that a person in the infected compartment will be infectious to mosquitoes during 4, 80, or 12 days. Because if one is infected, he's going to take a pill, and then after a while, the pill will make effect, and the person will not be infectious anymore to mosquitoes. Then we are considering 4, 80, or 12 days. And as we saw before, 30, 90, and 108 days duration for asymptomatic infections. With those assumptions, the proportion in our city of asymptomatic and symptomatic infections that are infectious to mosquitoes vary according to those graphs. So let's just take a look for the 30 days in asymptomatic infection duration. So we have here, let's say, with 4 days for the infected ones. We have 85% of people that are asymptomatic, while just the complementary, which is 15% here, which is infected individuals. And this varying according to the level, or to the duration of asymptomatic infections. Then what is the following question? Yeah. What is the relative contribution of symptomatic and asymptomatic infections to the whole transmission level? And then, so we went to many different articles and tried to get a parameter that informs us if someone is infected and comes a mosquito, and if it's asymptomatic, or let's call here infected. Asymptomatic is also infected, but just to follow the same rule. What is the relation between the infectiousness of an asymptomatic and an infected person? Then there are many, many articles talking about this. There is no fixed values. And then what we did, again, let's check different scenarios. We considered that the relative infectiousness between infected and asymptomatic is half, 1/10, and 1/3. Yeah? And then with those values and considering different asymptomatic durations, we have this scenario here. Where we are, we don't know. But we can see that if we are here, asymptomatic is the major contributor or the major contribution to the whole transmission. If you are here, the infected ones that are symptomatic are the main contributors to the whole transmission. But those values, 1/3, 1/10, half, and 30 days, 90 days, and 180 days, are kind of, are not out of the range that we saw in many studies, which means that we cannot neglect asymptomatic infections. There are possibilities that they are contributing a lot to the whole transmission. This is the main message of this work. This work was already accepted in PLOS computational biology since January, but it seems that malaria is even more neglected after coronavirus came up, so it stopped there for a while. So, a brief discussion because we don't have much time yet. First of all, if we do not consider risk heterogeneity in our model, we have different conclusions, yeah? Let's just take a look here in the partial immunity that we found. It's different with, and with this difference in the partial immunity will change the whole dynamics of the model. So, which may lead to wrong conclusions afterwards. We found this 20-80 rule. In our case, 20% of the population is responsible for 86% of the case of the transmission in the area. Here in Brazil, with low transmission, in a low transmission set, it seems that the population is acquiring partial immunity much slower than in settings with high transmission. As I said in the beginning, and was already said before, like we have relapses for P-vivax, but our model is not directly considering it, but our force of infection is contributing to this to this fact. Yeah, let's say a high-risk person maybe is someone that never takes Primaquine, that is the drug that prevent relapses. Yeah. So asymptomatic, and here is really important to emphasize, may constitute a major parasite reservoir. And with this, I just acknowledge the people that I'm working with, people that collect the data in the field, people from the Helmholtz Zentrum Institute from München that helped us with the with the model calibration, Professor Marcelo and Professor Gabriela Gomez, which are co-authors in this work. This is from the field side. Yeah.
Thank you. Questions?
Excuse me. Did you try other dependence device for the course infection?
Other.
Because, for example, in my family, the age dependence is exactly the opposite. The more younger child receives all the bits.
In which disease you mean? You said?
No, just mosquito bites. Just
mosquito bites. Yeah, like here, our assumption is that the body surface is related to the malaria transmission, and as was already saw in another field site in Africa. Yeah, like there is no. It was not observed that children is more susceptible to bites than adults for malaria or for Anopheles in this case. Yeah. Yeah, for this particular vector. Yeah.
Did you have any information about multiple exposures to malaria? Did you know within the study area that you collected? So from all the people that had malaria, do you know how many had multiple infections?
Yes, it's one of our data sets. Here. So we had, in 1 year, someone had up to 6. Yeah, six infections in the same year.
Okay.
Yeah. Okay.
Thank you very much for your presentation. Very interesting. I have 2 short questions. The first one, when you talk about the risk distribution, right? What is the physical dimension of the risk distribution? I mean, is it about the body surface? What are you exactly? What should I understand about the risk distribution? I didn't understand. Maybe I lost your explanation.
Yes. Please. So maybe I can come back here. Yeah, here. Yeah. So there are a lot of sources of risk heterogeneity. Yeah, as I mentioned here, and as we saw already in this statistical study that we made there. Then we comprise every heterogeneity and variables and risk factors in just one measure, that is the force of infection. Yeah, but then we multiply this force of infection by the risk, and then we have the low risk group and the high risk group. The high risk group, let's say, are the ones that have the risk factors from this study, have some behavioral characteristics, and is more attracted to mosquitoes than others. Yeah, and then those guys are in the high risk group. And let's say the low risk groups are rich people located in the city center that is not going to the forest. Like then the risk distribution comprise all the heterogeneous of the model.
Yeah, more or less. Because please go ahead to keep the final dimension of your equation.
No.
Do you understand my question?
Yeah, but like x is just a factor. It's like, yeah, we saw here the values. Yeah, so x is here. In this case, it's 4.64.
Just a proportion.
Yeah.
Okay.
Yeah.
So my second question is about when you showed us your asymptomatic graph, okay?
Yeah.
Do you have any real data about these asymptomatic people? Because what I know is it's very hard to estimate this.
Yeah, it's very hard to estimate this.
How did you compare
Yeah.
your model with the real data in this case?
So we still don't have the prevalence of asymptomatic infections. We know that it's around those values that we found here, but this is what is coming after. We are collecting this data. We are going to the field every 6 months and make an exam and collecting blood samples of 20% of the population, bringing back to the lab and analyzing, and then we are going to have this. And then what is interesting, that we are going to have this value. We can come here and get this value, which is the duration of asymptomatic infections.
Nice. So you are going to provide us the real data? Because you told us you are going to
Yes, I will. Sooner or later, it will come.
Okay, keep us updated.
Okay, sure.
Thank you very much.
Yeah, you're welcome.
Just to be honest, the last picture that you put on the thing, right, is that from, I imagine it's from the urban area of Marcelima, right? I'm not sure if the audience realize how different urban Marcelima is from typical urban areas.
Yeah, okay, so this is something that I should have emphasized. This is a city in the middle of the Amazon basin. So a urban area in the Amazon basin, a small city over there, is different than São Paulo downtown, yeah? So this is from there, is a bit different. And actually, this is a debate that goes around. What is urban, what is rural? This is always will play a role in the discussions, but we are considering this. I was there, yeah, and they have air conditioners and barcode readers in the supermarket. Definitely this is urban, right? Yeah. Okay.
Okay. Thank you again.
Okay. Thank you.
So please note we have a different schedule today. We start at 2:30.
Você se entende direito, mas você fez um primeiro modelo mais simples, que você citou seus dados.